All right, cool. So I see we've got about 18 people on the line, which is excellent. If you guys have questions, I believe you can submit those questions via Zoom, and I will do my best to answer them in real time, or if it makes more sense, I'll just do it right at the end of this presentation. I'm going to share my screen now and show you where all of the material for today can be found. I've put everything up on GitHub. The URL is here, and I will also see if I can paste this into the chat for everybody. There we go. So that URL has all of the content for today. And yeah, a quick note from Lauren, this webinar is being recorded and will be available online. So just heads up on that. So at this URL on GitHub, you can find all of the slides for today if you just click on this link. And that is where I will start. So I'm Max Joseph. I'm a data scientist at Earth Lab, and I'm also an open science architect for the North Central Climate Adaptation Science Center. Today I'm going to be talking about Research Compendia, a little bit about why you might want to build these, but mostly how you can build a research compendium. If anyone wants to get in touch with me, you can @ me on Twitter. I'm at MXWLJ, or you can contact me through GitHub. I'm at MBJoseph. All right, so let's dive right in. What is a research compendium? It's essentially a collection of digital components of a research project. So you can think of a compendium as being the sum of data and some code and maybe some text. And the reason why people are becoming more interested in research compendium really has to do a lot with reproducible research. So we know that the sciences are undergoing a reproducibility crisis and have been for the last decade or more. Research compendia are essentially, at the end of the day, trying to make our work more easy to reproduce. But this applies even beyond science. So if you're working for a consulting firm or a tech company and you need to write a report, it's also important that those reports are reproducible. So you can use a research compendium in science and elsewhere. And one thing that I want to note here is it's not just trying to make your work easy to reproduce for other people, but also easier for yourself to reproduce an analysis if you come back to it, a year, 2 years, or even in some cases, just a couple months later. The more work you put in to document and automate your project up front, the easier it will be to come back to that project later if you need to. In addition to reproducibility, compendia can make your work much more transparent because you can see exactly where all of your results are coming from, more reliable. If you can get that same result every single time you run your analysis, that's a good thing. Reusable, if your code is out there, other people can then borrow that code or adapt it for their own purposes. And visible, you can share your research compendium on GitHub or GitLab, tweet about it, and essentially broaden the reach of your work. In terms of how you organize a research compendium, there are 3 main principles, and you can adhere to these principles in lots of different ways. But the principles are: use some kind of conventional directory structure. You don't have to use the same one every time, but you want it to follow at least some convention and make some intuitive sense. Second principle is to separate the components of your project. So you want to have a place for data, a place for your methods or your scripts, and another place for your outputs that you're generating for your project. And then importantly, third, you also need to at least specify and maybe even deliver a computational environment. That is, what is the software that you need to actually run your code and reproduce your work? And throughout this presentation, I'll be providing some citations down here at the bottom. If you want to dig more into these details, these papers are really useful resources to get into why these principles are important and all the different ways that you might adhere to them or adapt them for your own use cases. So I'm going to start with a really basic example of what a research compendium might look like. This is essentially trying to show that you've got some folder or some directory called Compendium, and then within that folder, you've got another folder called Data, and that contains maybe a CSV file if you've got tabular data, and then a separate folder called Analysis, or maybe you've got a script. This could be a Python script, an R script, whatever other scripts. And then at the top level, you've got a README that maybe explains like how to run your analysis and what you need to install to actually get this all to work. So we can sort of check this box that we've got some kind of directory structure here. There's a data directory and analysis directory. Those are pretty self-explanatory. They're separate components. And we've described what the environment should be in this README file. But there are a lot of other components that are often useful to include in research compendia. And these are the components that I want to focus on today. There are two things that we just won't have time to cover today, and those are automated tests and interactivity. And I'll just briefly mention that there's a growing movement to actually structure analyses as packages, whether it's a Python package or an R package, which in some cases makes it really easy to write automated tests. And then for interactivity, I won't talk about how to do this, but I will show you an example at the end of the talk. So the most important thing to start out with, if you want people to actually use your analysis, you have to set some rules for how they can and cannot use your analysis. And the way that you set those rules is by choosing a license. If you're not a lawyer, and I'm assuming that most of us are not, there's a really great website called choosealicense.com. And it essentially will walk you through a variety of considerations to help you decide what the best license might be, given your project and given what you want people and what you don't want people to do with your code. But there are some sort of useful recommendations provided by this thing called the Reproducible Research Standard. And the recommendations provided by this standard are that for text and figures, so this would be like your manuscript maybe, and any figures that you generate, the recommendation is to use a CC BY Creative Commons license. For code, the recommendation is to use MIT license. And then if you're going to publish data, the recommendation under this standard is to just basically release it under a CC0 license. So make it available to the world, essentially. And if you want to dig into the details of this, Victoria Stodden has done a lot of great work to justify these recommendations and explore the implications that she lays out in this paper from 2009. Adding a license to your compendium is as easy as just adding a text file that's called license. And in most cases, you're going to add that at the top level of your directory. So now, this project, other people can reuse it. If you don't specify a license, then implicitly, you are holding copyright yourself, and it's not allowed for other people to take your code and repurpose it, for example. So specifying a license is an important technical detail, and it also signals to people that you've thought about how people might be able to reuse or adapt your code. Okay, so we've checked this box. We've got some rules for reuse. Another component that's really important is some logical and directory separation between the inputs to your project and the outputs, or things that you generate. So people often talk about raw data. They don't often talk about cooked data, but you could imagine that cooked data is like data that you've cleaned and generated. So if you wanted to keep some separation there, you might add a subdirectory in your data directory called raw, where you just put the raw data, and that's the data that you've maybe downloaded from the internet, or maybe data that you've collected from the field. And the idea is you want to retain that raw data in its original form. You don't want to go in and modify it, but if you do need to modify it or clean it in some way, you can save that in a different place, like a directory called clean, for example. And this is important because you always want to make sure that you retain the original raw data so that you can go back to that as a starting point if necessary. And additionally, you might have other outputs like figures, right? So in many cases, we're generating plots, and you might want to put those figures in their own directory. So here I've added another directory to our compendium called figures, and in there I've got like an awesome plot. And as an aside, this is a really good time to talk about what to track and what not to track with Git. If you're not familiar with Git, you can just ignore this for now, but if you do know a bit about Git, you might know that you don't always want to track the outputs that you're generating, right? So for example, if this awesome plot is generated every time we run the code, we don't necessarily need to track that using version control, and same for this clean data set. If we can create this from the raw data, maybe we don't want to always keep track of how it changes over time. And so one thing you can do to use or to ignore those files is to use a gitignore file. So a gitignore file is just a text file that is called .gitignore, and that dot is important. It indicates this is a hidden file, and the contents of this file might look like this. So this gitignore is saying, ignore this clean subdirectory within the data directory, and ignore any of the contents of the figures folder that have something .png. So if we add a gitignore file to this compendium, you can add that at the top level. And so now we've got our gitignore file. We've got good separation between inputs and outputs. And so we can check this box of separating input and output, and furthermore, not tracking the output, because we can always generate it from the same inputs. All right, so I'm assuming that a lot of you know Python and have used Python, and by extension, probably a good fraction of you have run into some challenges dealing with Python environments and installations at some point. And this is not necessarily specific to Python. This happens with a lot of other languages, and it's really important that you have an unambiguous specification of your computational environment so that people can reproduce your analysis essentially using the same packages that you've used. And there are a lot of ways to specify an environment. So Python in particular has a lot of different options, including a requirements.txt file, an environment YAML file, setup.py, a pip file. If you use R, the equivalent would be like a description file where you can say what packages your work depends on. And so today I'm going to focus mostly on this environment YML file under the assumption that many of us are using Conda to deal with Python dependency management. An environment.yml file, it's a YAML file. It's essentially just a text file where you've got the name of a Conda environment and then whatever dependencies you need to install in that environment. So this is a fairly simple one. I'm just specifying that I want to use pandas and matplotlib. And I'm also specifying which version of Python that I want to use. And if you want to be really specific, you can specify down to Python 3.8.1 or specify specific versions of pandas and matplotlib, which is a good idea in many cases if you want to be really sure that people are building your project with the same exact package versions that you used originally. And if you're not familiar with Conda environments, I will just say that this text file basically tells your computer exactly what dependencies you should install and what versions of those dependencies you should install. I want to make a quick shout out to Docker, which we talked about specifying an environment. Docker is a way to actually provide an executable environment. We don't really have time to get into it today, but at least in our own work at EarthLab, we find that the combination of Docker and Conda environments is pretty useful to try to get something that will have the same set of packages that can run essentially anywhere. So I'll just leave it at that. And if we add an environment file to our compendium, typically that's just in the top level directory. So now we're starting to get something that keeps track of of inputs and outputs, has rules for reuse, and specifies unambiguously what that environment should look like. Okay, so the next thing is coordinating multiple steps. So previously, I've sort of simplified what a project might look like. It's probably rare that for a real project, you would have just one single script that does all of your analysis, right? In many cases, a project actually consists of multiple sequential steps. So for example, you might actually have like 3 scripts in your analysis directory. One that gets some data, maybe from the internet, another one that processes that data or cleans it in some way, and then another that actually does some maybe exploratory data analysis or fits some models. And managing these multiple steps in an analysis turns out to be a really important and really useful component of a research compendium. So here's a graphical representation of what like a fairly simple multi-step workflow might look like. The first script that I need to run is called get data, and all it's going to do is generate a CSV file called data, and then this is the raw data, right? I need to do some cleaning on that, so I combine the raw data with another script called clean data. So clean data, you could imagine, maybe loads the raw data and filters it, and then saves some new output called clean data. And then finally, my third script maybe loads the clean data, generates some visualizations, and then saves something called awesomeplot.png. So this workflow essentially has 3 steps: get data, clean data, EDA. And every one of those steps generates one output. So first output is the raw data that we download. Second output is the cleaned data, and the third output is this plot. And representing this workflow as a graph is actually a really useful construct. So let's say that I need to update the way that I have cleaned my data. Maybe I realize that I need to filter on date or something like that. So I update this script, 02 clean data. What part of the workflow actually needs to be executed again? So you can think about this graph, and if my get data script hasn't changed, then this data file also shouldn't change. It turns out that I really only need to rerun 2/3 of this workflow. Everything starting from clean data and then the downstream work from there. And so this is a way to be more efficient with your workflow. So instead of rerunning the whole thing, you might think about, is there a way to only rerun the part of my workflow that could be updated given the change to this file? And there are a lot of tools, it turns out, to do that. In a simple setting, you could imagine writing like a main script. Maybe this is a Python script. Maybe this is a shell script. And in those scripts, you could check to see, like, when did this file change? And if it changed more recently than this other one, execute it. But there are a lot of great tools that will do that work for you. They're a little bit fancier, but I'm going to talk about GNU Make for the most part because it's a very general purpose. It's language agnostic. If you're using Python extensively and more comfortable with Python, you might check out SnakeMake. And if you're more of an R user, there's a great package called Drake, which will do this for you as well. All right, so on to GNU Make. GNU Make is a bit of software that essentially manages this workflow for you and figures out what needs to be executed. The main component for Research Compendium is a makefile. A makefile essentially specifies the relationships among files, so what depends on what, and then how to generate the output. And so that's essentially like, if you go back to our cool plot, what are the dependencies of that? If you go back to the raw data, what are the dependencies of that? And that's what's specified in a makefile. So here's our workflow again. I want to walk through how you might write a makefile for this workflow. The syntax for a makefile is shown here. You've got a target, which is essentially what is the file or what are the files that you want to generate, and then a colon, and then prerequisites, which are essentially the dependencies of that file. So what does the file need to be created? And then with a tab, recipe. So how do you actually generate the target? And so I'm going to start with just the first step in our workflow. The first target is this raw data file, data.csv, and then I'm adding a colon. And what does data.csv depend on? Well, it depends on this get data, and this should be .py, not CSV, sorry about that. Depends on this getData.py file. And then the recipe, which is how do you actually generate data.csv? In this case, this would be Python 01 getData.py. If you try to execute a CSV file in Python, probably you will not have good luck. In any case, you can see how this matches the target, colon, prerequisites, and then recipe syntax. And so now let's move on to the next step. Clean data.csv is our next target. That depends on data.csv, and you can see that dependency structure here in this figure. And it also depends on clean data.py. And to actually generate clean data, what we're going to do is use Python to execute this script, 02 clean data.py. Okay, and I'll also mention here, I have ordered these in sort of like a chronological order, but actually for make, it doesn't really matter. You could swap the order of these two rules and you would still have an equivalent makefile. And now our third step, the final target, is this awesome plot.png. That depends on clean data, and it depends on this Python script. And in order to create our awesome plot, we can use Python to execute that script. And so this is the syntax for our makefile. And what NewMake does under the hood is it takes this makefile and it actually builds a representation a lot like this graph. If you're familiar with the concept of a DAG or a directed acyclic graph, that's essentially what Make is using under the hood to represent the dependency structure among our inputs and outputs. Okay, so our updated compendium would look something like this, where we have another file now at the top level directory called a makefile. And that is going to be able to coordinate all of these scripts, generate these outputs, and generate our plot. And this makefile that we just went through is fairly simple, but Make is a very general purpose program. You can make very elaborate makefiles to keep track of complex workflows. Okay, so now we've coordinated multiple steps of our compendium. And the last thing that I want to highlight is that you can actually generate like a scientific paper or a manuscript or maybe a report using a research compendium. And I'll show you a bunch of options. Pandoc is a really general purpose tool that you can use. For instance, if you're writing a report in Markdown or in restructured text, you can export to PDF, to Word format, to HTML. And then if you're using R or Python, you can also use R Markdown to do something really similar. R Markdown, I'll also point out, has great support for Python and sort of a really nice community that is building packages specifically for academic publishing. So you can get like journal article templates that work really well with R Markdown, for example. I've written, I think, 4 or 5 scientific papers using this approach with R Markdown, and it gives you a lot of control over the details of how you're exporting, for instance, PDF or LaTeX output. And then NB-convert is another great tool in the Jupyter ecosystem that you can use to export to PDF or HTML. I'm going to focus on the more generic sort of tool of Pandoc for today. And I will just say for now, and I'll show you an example later, that all you really need to do to make this happen is add a markdown file. That would be like your paper, and then edit your make file a little bit, and then you can essentially just add a paper generation step to the end of your workflow. Okay, so those are some key components, and let's go through some examples now. I will ask that if you guys are wanting to follow along, go to the URL for this talk, which I will paste again into the chat, just so that you all have it. Oh, and I see 11 chat things now. Sorry, I, for some reason, couldn't see any of the chats while I was presenting. But this seems like a good point maybe to address any questions. So I will do that now. One of these questions, okay. I'm seeing a question about managing YAML separately from Docker. And Leah, yes, I agree with Leah's point that sometimes it is nice to be able to separately manage an environment.yml file from a Docker file. And one of the advantages of that is that you can use your environment file anywhere, even if somebody doesn't have Docker. But if somebody does have Docker, they can just use the Docker file. So you have a little bit more flexibility if you've got an environment YAML file separate from your Docker file, if you're familiar with Docker. But you certainly can use both together, or you can absorb the contents of your environment file into your Docker file. Both of those are valid options. Oh, and I'm seeing also that there are more questions in the Q&A. For some reason, I can't see any questions in the Q&A. So if...
I can read them out loud if you
That would be great. Yeah.
Okay, we're still figuring out the tech. So
yeah.
Here's the first one from Anonymous. For data that you did not collect yourself, it seems like it is more important to provide data access provenance, URLs or API calls or citations, etc., in addition to putting the data in the compendium itself. Do you have any guidance on the best practices for data provenance?
Yeah, that's a really good question. So this is there's not a really simple answer here, but my own perspective on this is that you definitely want to retain all of the code, API calls, etc., that you use to acquire the data and provide that code in your compendium. But it's also a good idea to archive the data that you actually use, even if it's not your own data. But that does require that you keep track of like the associated metadata, et cetera, and clearly make the link back to the data that you used and how you actually got that data. So if you're familiar, for instance, with Open Science Framework, they have some pretty good functionality to actually archive data along with code. So that might be a good option if you're finding yourself in that type of situation. How about the, go ahead.
The next question, or were you going to say something?
No, I was going to say next question.
Okay. Do you suggest, and you started to answer this, do you suggest having the YAML file be a part of your Git repo? So I think that's with the rest of the compendium pieces.
Yeah, I do recommend that. That's really useful, especially as a way to track any changes to your YAML file. It's nice to have that under version control.
Okay, and then the next question is it typical / recommended to have the scripts numbered like in the example, or is that just how you happen to label them?
Yeah, I think there are probably differing opinions out there in the community. In this case, I was trying to be really explicit about the order of these steps, and so I included it. Um, so that's one advantage. The disadvantage is if you ever need to go back and like insert an intermediate step, then you have to rename all of these other files. So there are pros and cons. But for the purposes of today, I was trying to just be really clear about this idea of a set of sequential steps. And so that's why I added those number prefixes to the scripts. Okay, and I see the last question. The makefile example was organized as a function of the output. By this, I don't mean the order in the makefile, but that the elements were of the form output is a function of x, y, z. Is this typical? Yeah, so the traditional syntax for a makefile is, and I'll share my screen again here, go back to the slides. So this set of a target and then colon, prerequisites, recipe, this is called a rule in the make program, and a rule basically tells make how to generate the target. So yeah, I would say that is sort of the canonical syntax for generating files using make. Okay, and are there any other questions before we look at an example? Okay, awesome. All right, so let's go back to GitHub, where we've got a real life working example. So I'm going to go back to this GitHub repo, and there's a subdirectory in here called example compendium. So I'm going to click in there, and here you will see essentially like all of the components that I just outlined, as well as some additional information in the README. So the first thing in this README is telling users what are the prerequisites that they'll need to actually execute my research compendium. And then I promised that I would show some interactive stuff. And so if you want to actually try this out interactively, you can click on this Launch Binder button. And this is nice as a way to prevent users from needing to install stuff on their own machines. So Binder is a way essentially to share your code, and you can specify an environment so that users can go in and actually interactively play with your code or run it without having to install, for example, like Conda on their local machines, or having to install Pandoc or LaTeX or anything like that. So depending on how many people are using it, sometimes it takes a while to spin up, but mine spun up relatively quickly. This is what Binder looks like. So it actually, by default, will open up a Jupyter Notebook session, which is amazing, and it's free. So I definitely recommend checking that out if you do want to share some code. And for today, we don't really have any Jupyter Notebooks, but we are running stuff in a terminal. So I want to open a terminal session. I'm going to go to this new button over here, and then click on terminal. Okay, and this then opens up a terminal, and I can see where I am by typing pwd. So by default, you're in this Jovian directory, but if I type ls, I'll see all of the files that were in my GitHub repository. And I'm going to split my screen here a little bit just so that I can simultaneously look at the instructions that I provided for the compendium and show you the terminal. So on the right here, I've got my example compendium here. Okay, so here I am, just to remind ourselves, I've got my instructions on the right and my interactive binder session on the left. So I'm just going to walk through the instructions here to reproduce the analysis with my compendium. So the first thing that I need to do is actually enter this example compendium directory. So I will follow my own instructions and type cd example compendium. And now if I look at what's in that directory, I see that I've got my analysis folder, my data folder, everything else. And because I'm using Conda, I can create a Conda environment using Conda env create f, and then my environment. F just means file, so you're pointing Conda to an environment YAML file, and from that environment file, it will actually generate your environment. And just to show you what the actual environment file looks like here, I'm giving it a name, Denver Traffic, for reasons that will become clear soon, and specifying that I need to have Python 3.8, pandas, matplotlib, as well as make and pandoc. And so one of the really nice things about Conda is it doesn't just install Python or Python libraries, but you can also install system level libraries like make and pandoc as well. So it's a great tool if you do need to install those, in some cases, harder to install packages. And so you can see here that it's installing a bunch of stuff. Oftentimes you might find that your binder instances they're not lightning fast, but they're typically fast enough to get the job done in like small to medium data settings, and it's free. So yeah, this will be setting up the environment for us. And since I can't see the questions and I can't see the chat, I'm just gonna suggest that if there are questions or questions in the chat that come up, Leah, feel free to interject as we're going through this demo. And if anyone is curious about Binder, I'll also mention while this is installing that setting Binder up for your repository is super easy. If you go to mybinder.org, what you can do is just paste in a GitHub repository name or URL, and under many circumstances, Binder will be able to automatically set up your environment for you, especially if you're using like a conventional means to specify an environment, such as an environment YAML file or requirements.txt file. So definitely check Binder out if this seems interesting. Now that I've finished installing my Conda environment, I can activate it using Conda activate Denver Traffic. Cool. And so now all I need to do to run my analysis, to run those 3 Python scripts and generate a report is type make, which is really handy, right? It's like the golden dream of just having a go button where you can execute one command and kick off an entire workflow. And so you can see essentially what's happening. I typed make, and I can see the rules or the recipes that are being executed for each rule. So now I'm executing this first get data script, which I will show you while it's running. So get data, the city of Denver provides accident level traffic accident data. So like on any day, if there were 14 accidents, you will get 14 reports, 1 per accident. And you can download all of the accident data from this URL. What I've done in the second step of cleaning the data is I'm just summing across days, and then EDA, I'm making a plot and then generating a PDF report, which I will show you to see exactly what it is that we just put together. So here's my example compendium directory in my Jupyter Notebook file browser. If I click on paper, I can look at the source file. This is the markdown file. It's very small, but I just want to highlight that you can use LaTeX commands. So this use package left line numbers and then specify line numbers. And all of this is just markdown syntax other than that. And I'm inserting my figure. Let's take a look at what this generated PDF looks like. Here we go. So this is the PDF that we've generated. And essentially all that I did is I took the Denver traffic data, I subset it to everything after January 1st of this year, which is on the x-axis. Every x-axis is a different day. The y-axis is the number of accidents, and I've colored like Saturday and Sunday are red, during the work week is blue. And so a couple of things to note is that typically the number of accidents on the weekend is lower than during the weekday, which makes sense. A lot of people are commuting on the weekdays. Another thing that's consistent with my own experience commuting is accidents tend to be more abundant, more common on average toward the end of the week, especially on Fridays. People want to get home. And then something weird has happened. The most recent data that I could get only went to March 12th, but you can see, when people are probably driving less and maybe even driving more carefully. This is the previous week, not this week, but last week. The number of accidents way down, sort of in the range that you would expect on weekends. So a lot of us, I'm assuming, are watching this webinar from home and out on the streets getting in car accidents. So that is essentially the demo part of this. If you want to check out any of the details, everything is on GitHub, and so you should feel free to fork this repository if you want to play with it. You can use this example compendium as a template for your own work if you want to. And with that, I will stop sharing and check out any questions. And apologies, like I said, I can't see the Q&A window, so I may need some help from Leah or others if you want to paste into the chat.
Yeah, so right now, I don't see anything in the Q&A, but if anyone has any questions, I think Lauren can unmute you if you wanted to verbally ask questions, or you can absolutely post in the Q&A. Oh, here's a question. How was the report generated? What step in the code did this occur?
Yeah, that's a great question. I'll show you. So let me go back to the original GitHub repo, and I'll show you what the actual makefile looks like. So the makefile that I outlined in the talk is a bit of a simplification just to make it easy to understand. This is what the actual makefile is. I'll zoom in here. And so you can see the rule for building the report is here on lines 13 and 14. So the file that I'm trying to make is paper/report.pdf. The files that depends on include the report markdown file and the figure. And I'm using a tool called Pandoc to actually compile that markdown file into the PDF. So this is the actual code that's being used to generate that PDF. And when I typed make in the terminal, essentially what that did is it looked for this rule called all, which collects all of the final outputs from your workflow. So in this simple example, the only final output is this report.pdf. So typing make was equivalent to typing make, let me clear this out. When I typed make, now it's saying there's nothing to be done for all because I haven't updated anything. But that would be identical to make, what did I call it? Paper/report, I think. Yeah, .pdf. So you can make specific targets if you type make paper/report.pdf. And this is telling me that it's up to date. There's really no reason to update that file. But if I were to go and modify my actual report, like this is some text I forgot, and then save that, if I type make again, it will rebuild the output and it will only execute the steps that need to be re-executed. So you can see if I type make, all that it does is run that final step of converting the report markdown file to the report PDF. And graphically, you can see that dependency structure here as well. So if the only file that changes is report.md, then we don't need to rerun any of our Python scripts. All we have to rerun is this final step to generate that PDF report. That's a great question.
Okay, are there any other, there's nothing in the chat right now. Are there any other questions? You guys can, again, ask verbally. We can unmute you. You can type in the Q&A or type in the chat. Oh, here's a question. Leslie says, how did you generate the schematic?
Oh yeah, I just used Inkscape, which is like a open source vector graphics editing program. Yeah, nothing too fancy there, but yeah, it's free and open source, so you should be able to get it pretty easily. It's kind of like a free-ish version of Adobe Illustrator, but not quite as fancy as Illustrator. And if there are no other questions, I'll just wrap up by highlighting some other really good resources that I like. So one of them is this R-OpenSci reproducibility guide. This is written for the R-OpenSci community, but honestly, a lot of it's not too specific to the R programming languages. If you guys are writing in Python, you'll find a lot of really great stuff there. Another resource that I like, not just about compendia, but about like open research in general, is the Turing Way. They have a chapter on research compendia, but they get into a lot of other really important topics, including some of the issues around like data provenance and data management that came up earlier. So check that out. Another sort of neat thing that you can do if you want to, in some sense, look through like a research compendium zoo is you can search for research compendia on GitHub, and you'll find some real world examples. So for example, I really like this one. If any of you are familiar with Carl Boettiger, he's been sort of at the forefront of a lot of the advocacy and thought leadership around research compendia. But you'll be able to see, for example, like he's got his whole paper in here written in our Markdown, and this is a journal article. So you might find it useful to actually look through some real world examples. There's also an example in here. This one has a combination of R and Python and a bit more of like a complicated makefile because this is a workflow with a lot of different steps. And so if you're looking to see like what do these research compendia actually look like outside of this sort of simplified webinar setting, you can find them on GitHub essentially by just searching for this research-compendium tag. And you'll find a lot of really great examples there. And then finally, there's also a research compendium landing page that has some great references if you want to dig into some of the literature around this, as well as like workshops and packages to support building research compendia. And with that, I will just say thanks. If there are any other questions, we can answer those now. I also want to mention this work was funded by a National Science Foundation Harnessing the Data Revolution grant that was awarded to Leah and her team. So thanks for inviting me to come talk about research compendia. And I'll answer any questions if we have any.
Thank you, Max. That was awesome. And there's one more question here from Anna. So it says, can you speak to good ways to dynamically collaborate on the paper portion? For example, how do you envision co-authors making comments and then allowing responses, interactions that I'm used to doing through Google Docs or emailing doc files?
Yeah, that's a great question. So there are a lot of options here, and it kind of depends on who you're collaborating with. So if your collaborators are very Git savvy and they understand how to use like Markdown and R Markdown, then you can collaborate through Git, like through pull requests, opening issues, etc., forking a repository, making some changes, and then submitting a PR back. If your collaborators are a little more comfortable with Microsoft Word, you can export to a Word format and send that Word document to your collaborators and have them make comments, make changes, and then use that to revise the source file. There's also Overleaf, which is a great collaborative LaTeX editor if you want to write papers with your collaborators in LaTeX. And then there's also there are a couple of packages that try to simplify the process of going back and forth between R Markdown and Word documents as well. So there are a lot of options, but I think one of the key components is just knowing what your collaborators feel most comfortable with and trying to make sure that they can contribute to the paper in a meaningful way. And that really depends on like what tools do they know, and are they in some cases willing to invest in learning a new tool if they think it's going to be useful for them. That's a great question.
Okay, awesome. Any more questions from anyone? Oh, I see one. So it's in the Q&A. Oh, it's a resource from Andrew. I'm going to put this in the chat as well. So it's a resource on effective computation in physics. I just put it in the chat. It's like a book.
Cool. Yeah, I haven't seen this before, but it looks neat.
Awesome. Any other questions or comments from anyone? Oh, here we go. Another question. Can you briefly explain the clean step in the makefile?
Yeah, happy to. So the clean step, let me pull up this makefile again so that we are all talking about the same thing. So here's the makefile for the compendium that we were talking about. And down here at the bottom, you can see this whole thing is called a rule. The target is called clean, and this is like a special target for make. And it essentially provides a way to delete all of the generated output. So you can see that I'm removing or deleting the PDF report, removing the PNG, and then removing these CSV files. And so if you ever need to like start over with your project, what you can do is type make clean. And so I'll show you, this is my terminal session with my binder. And if I type make clean, it removes all of those things. And so now I have basically started back from zero. And if I type make, it rebuilds the whole thing. So make clean just provides a way to get rid of all the generated content, and if necessary, start over from scratch with your analysis.
Great. Any other questions? We've got about a couple minutes left. Okay, well, I just want to say thank you, Max. That was amazing, amazing talk. And just so everyone knows, we did record this today, and we are going to be placing it up on our Earth Lab YouTube channel, so you can share it or revisit it in the future if you'd like. And then, of course, you've got Max's GitHub repository that you could check out some of the steps that he reviewed today. And so thank you everyone for coming. And again, thank you, Max, for putting together such an excellent presentation and sharing it with everyone.
Of course, yeah, thanks for the invite. And thanks everyone for attending. I hope you have a great rest of your day and stay safe out there.
Yeah, stay safe. Lots of thank yous coming in the chat. See you guys.
All right, see ya.